Okay,
Well, I should make one about Helen Keller, I feel like.
that'll be on the video. Okay. Here we go, folks. Um, so we talked on Friday. A continuous spectrum is like in terms of this, it's all the wavelengths from one point to another. So like with no breaks in it, just you could have any number, any point along between these 2 points. Okay, and this is the visible spectrum, like what we can see. Now, as it says in the notes, a line spectrum is a spectrum that contains only certain colors or wavelengths. So so we know that like basically white light will give us a continuous spectrum, right? We talked about that. Like white light is basically has all of the colors combined together. That's what our eye registers. So other colors that we see have less or fewer wavelengths than a whole continuous spectrum. Like it doesn't have all of them. So in other words, if I look at some of you guys wearing red, basically, I know it's the red row. So what I'm, again, we talked about all this, right? What we're seeing is light reflecting off of it coming into our eyes or whatever. But the reason we're seeing red is because those, clothes or dyes or whatever are absorbing certain wavelengths and reflecting others. So it's reflecting stuff more in the red, orange in here, and it's probably absorbing a lot of this. So what's actually coming into our eyes when we see that is just a certain set of wavelengths. Okay, and then what you can do is you can take that color and you can break it up into certain individual wavelengths that then make it up. So like white light is all this together. Here, let me see if I can give you a question. Let me see if we can pull up like so a line spectrum of a red color might look something like this, where there's like it combines together to give you red, but these would be all the individual different ones that are there, but it wouldn't be all of them. Does that make sense? Sort of. So the line spectrum is basically what they've done is they've taken the continuous spectrum, and they're only showing the lines that are present out of that whole thing. Does that make sense somewhat? Okay. So, and we talked about like elements. Each element has a unique line spectrum, like fingerprints, right? Did I mention that or no? I can't remember what. So like, okay, so we know that people can be identified by fingerprints, right? So the way that people are identified by fingerprints, though, is like if you were to look at your fingers, you can see, you can see like different like arches and tents and whorls and stuff like that, right?
Now, don't have whorls. They're just like this. It's boring.
Okay, so if you look, like somebody else might have the exact same arch or tent or whorl, but what it is about a fingerprint, it's not just the one single mark. It's all of the different ones and the order they're in and where they're found and stuff like that. So like for those of you that maybe watch like the murder shows and all that kind of stuff like I do, they talk about fingerprint matches, and they need a certain number of points to be to be a reliable match. Like a 3-point match doesn't work. That's like a partial, like that doesn't prove that it's that person's, because there's other people that could have 3 of those points. So you need like I don't know what the standard is, like 6 or 7-point match in order to conclusively say that that's, and what they mean are just different unique things on their fingerprint that are in certain spots. So yeah.
The best time to murder someone would be when like you're old because like your fingerprints start to like go away because your hands get like clammy and disgusting.
I'm gonna kill someone when I get older.
I have no idea if I'm disturbed or impressed that you thought about that.
Because like old people, the reason why they have such a hard time like touching a phone screen is because their finger pads have like softened out, like they're not as hard.
Well, and it does I think too your skin loses some of its elasticity as you get older, and you stop producing uh your body stops producing it like oil and stuff as much. That's why your skin dries out more. So like the reason that we leave fingerprints is not really actually like your fingers themselves don't really produce like the oils and stuff that you leave the fingerprints with. It usually comes from other places on your body, like your face, it's like comes from like touching things, stuff like that, like touching other parts of your body and stuff. So if you're, as like you get older, your skin becomes less pliable, so it's you wouldn't leave a fingerprint as easily, and you also would, if your skin isn't as um, I don't know, for lack of a better word, moist. Like it dries out somewhat, like as you get older, and that would help prevent from leaving fingerprints as well. So, yes, you're right.
People watching the video are gonna have a fun time today.
They'll have something. Okay, so all right, line spectrum. Now, there's a model. So if we go back to like models of the atom, and I think we mentioned this like a long, long time ago, like way first semester. There was a guy named Niels Bohr that had a model of the hydrogen atom. He used what's called a planetary model to demonstrate energy gains and losses by electrons. So the Bohr model, okay, looks something kind of like this. He had a like a solid nucleus with protons. And then he had the energy levels where the electrons are found. So that's enough. You guys get the idea. I don't need to do a billion levels. But so basically, you have a solid nucleus, and in which the protons are contained, and then you have electrons orbiting around the outside. And these it's called the planetary model because it looks like a solar system with the planets. This is an N. I'm sorry, guys. It's like kind of I don't know. Maybe I should. Can you see that, or should I go over it in black pen? Can you guys see that, or okay? Yeah. Pencil doesn't always work through. So the electrons would be in the energy levels, and then you have the center. So this is called the planetary model or solar system model because you have like the nucleus in the center, and then everything kind of orbiting around. And so the quantum number n represents the principal energy levels in the atom, the main energy levels. N equals 1 represents the first energy level. N equals 2 represents the second energy level, etc. The ground state is the lowest energy level. So the ground state, it says represented by N equals 1, and that's partially correct. The ground state really is when all the electrons are in the lowest possible positions they can be in. So if you've got more than just in the first one, you can have a ground state and other stuff too, but it's got to be in the lowest possible spots. So yeah.
And the little circle in the middle, is that
That's a P for protons. Yeah. Yep. And then if electrons are in an excited state, it's excited states would be energy levels with higher amounts of energy, represented by N equals 2, N equals 3, N equals 4, and so on. So to simplify things, we're just going to call ground state like the n equals 1, and then all the other energy levels would be considered excited states. Okay? You good with that? Okay. So we've got some definitions here that are important to know when we're talking about this stuff. There is a difference between the word orbit and orbital. Okay? An orbit is a fixed path an object travels around a central object or point. So this is kind of like the planetary model, where you've got the nucleus in the center and then electrons orbiting around in fixed paths. That would be the idea of an orbit. So like, the moon orbits the Earth, or the Earth orbits the sun, like that kind of idea. An orbital is a region around a nucleus where an electron with a specific energy is likely to be found. So I'm sure that the orbital comes from orbit, because the original idea was that electrons orbited around the nucleus. But an orbital is like an area. So, for example, this kind of graded area here would represent an orbital. This right here. Or if this is the nucleus here, this could represent an orbital, these areas here. All right, what is what does all this have to do with energy and stuff like that? Okay, so let me ask you guys this kind of. Let's go back to some of the ideas we were talking about Friday. We talked about if you vaporize or burn different elements, they give you different colors, right? Did I find this on Friday? Had I found this or not?
Oh, I have an entire 25 pack of those.
You did
Okay.
find it, buddy.
I did or didn't? Oh, okay. So I did find this. This is what I was talking about the different colors. You throw in the flame. So if you look, so this basically you throw it in and it changes. When it burns, it makes the flames different colors, right? If you look at the ingredients, copper sulfate, sodium chloride, potassium chloride. Sodium chloride is like table salt. Potassium chloride is just another version of salt. Like that's actually a lot of the ice melt that they have for ice melting, in the winter, you put on your driveway. There's some versions of that that'll be potassium chloride. Copper sulfate. Copper sulfate is just another mixture. It's got copper in it. Obviously, it looks very similar to the copper chloride that you guys used when you did the aluminum wire thing. It's like a blue color, kind of like that. But if you can see, they've got different elements, and that's what gives the different colors when they burn. Yeah.
The way that my family used to do it is we would take a copper tube, and then we'd take a hose and put the copper in the hose, and then you throw it in the fire.
You throw in a hose, and you burn the copper and the hose. Huh.
Yeah.
Why would you throw it in the hose?
I don't know. Somehow that made it better or last longer.
Last longer or something. That's interesting. Yeah. So what it would give off what color usually?
Green and blue usually.
Yep. Yeah. So and that's like a specific color unique to copper. Other things will give off similar colors, but if you broke it down into that line spectrum, you'd find that there would be some differences. So we know that elements give off colors, right? Now, why did we say they give off different colors? Because they have what? Different, or I guess maybe I should say it as the fact that they give off different colors tells us what about the energy that they're giving off. Go back to the, if you can remember back to the photoelectric effect. Different colored light, some ejected electrons, some didn't. Anybody remember why we said that happened? Yeah. Yeah, good. And different wavelengths told us that the lights have different amounts of energy. Yeah, the packets of energy are different size, different amounts of energy, right? So different colors tell us different amounts of energy being given off. Everybody good with that idea? So, if we go back to this, what we're really starting to examine with this is why. Why are different atoms giving off different colors of energy? Okay, and that has to do with the electrons. So that's why, just to give you a background for like why are we talking about all this, it's because the electrons are what deals with the energy. So understanding where the electrons are in the atom is important to understanding how they use energy and where it goes and where it comes from and stuff like that. Okay. All right. We have some other definitions here. Matter waves, particles that exhibit wave-like behavior. This is observed when matter is extremely small. For example, a stream of electrons. So remember we talked about the dual nature of radiant energy where light can act as both waves and particles. Well, what they found, and remember that was like when it's really small, right? When light is really small is when we can see that. So we have this. The flip side, matter can actually have waves, you can see and exhibit wave-like behavior. And you observe that when matter is really small. For example, a stream of electrons. We said electrons are really small. You get a stream of electrons and they actually start having wave-like behavior. They have amplitude, they have wavelength, stuff like that. So like you get a stream of electrons and you start getting things like wavelength, amplitude, stuff like that. Okay, but only when they're really small is when you observe it. So it's kind of like it's like the matter version of the dual nature of radiant light. Okay. All right. Now we get to some weird stuff. Anybody ever heard of Heisenberg's uncertainty principle?
Yeah, it says that both the position and the momentum of the moving.
Yeah, you can. Okay. Yeah. Okay. Because the way that they observe them is impacted by the movement or whatever, right? Type of deal. Yeah. So Heisenberg's uncertainty principle comes down to how do we observe things, but how do we observe but talking about it on a really, really, really small level. So we've already talked about what happens when we see something. Like how do we see stuff? And there's our eyes, right? Good.
Which is a bad.
So light reflects off of it and enters into our eyes. Let's talk about other ways of observing things, like anybody fish? Okay, you've got those the fish finder things.
Yeah.
How do those work?
I think it's off like GPS and that, or I don't know. It's like,
Like they find the fish.
It says like waves.
Yeah, basically, I don't know. I think is it sonar,
Yeah. It's not
right? So they send out sonar signals, and basically what happens is um, the signal goes out, right? So you've got the signal in your boat. Um, so you've got the signal that gets sent out. Okay, so like this would be the signal. And what happens is it keeps traveling in a straight line out until it hits something. Once it hits something, it bounces back.
So does it call it a fish then? Like it could be a rock and it says it's a fish.
Well, so what happens? Have you guys have seen those? I don't even know what they're. It's kind of like a toy or whatever thing, but like where it's got like all the different. They look like nails. They're not really nails. You can put your hand underneath it, and it like you push up, and it makes it look like your hand on the top, right? I don't even know what that thing's called, but like that type of deal. That's kind of what sonar does. Is it goes, and when it hits, it bounces back, and then the machine records how long it takes how long it takes the signal to get back, and based on how long, it makes a map, and it just records a map of like, oh hey, there's something there, and so when you get all of these signals, coming back, you can get the shape and the like the depth and the shape and stuff like that from it, because you can see how long the other signals are bouncing and stuff, or how long it takes the other signals to hit and bounce back and things like that. So that's another way of observing something. Like you're not actually seeing it, but you're making an observation, and it's based off of something striking and coming back and giving you something you can record, right? So, so the point to talk about this is so think about on a really, really small level, right? Light or some kind of signal has to go and basically strike an object, or somehow, strike or reflect off of an object, and it has to come back to something that can record it, right? So in order for us to observe the position, of an object, something has to hit the object and be recorded, reflect off of hit, right? Everybody's good with that idea? Okay. If we talk about this on a very, very small level, remember we talked about the Compton effect? About the photon light striking the electron and moving it? So the idea is that it says here, there's an inherent limitation to knowing both where the particle is and how it is moving. So that's because when light, or whatever you're measuring, or whatever you're observing it with, whenever it strikes the object, it actually changes the movement. So you can know where it was at a certain point, but because the action of observing it changes the momentum, you can't really know where it was going. Or you can measure where it was like you can measure the rate of it, but you can't know where it is at exactly that point. Okay? You can know one or the other, but you can't know both because the action of observing it alters it. Now, again, where do we worry about this? So, like, if you're, if you run track or something, like, well, you can't know both where, like, you're at the finish line and what the speed is. Like, no, like that's not. This has really, it has applications that you can then use for things to like trans to like use for things that you make for real life stuff. But like this actual idea, Heisenberg's uncertainty principle, doesn't really have a um, it's only important on this level. Like it only matters on a really crazy small level. We don't worry about it in everyday life because it's such a small amount that it doesn't factor in. Okay, so but remember, we're talking about trying to figure out where electrons are, and that's where it gets to be a real pain. Because if we're trying to find where electrons are, and they can be moved by the things that we find them with, like that becomes really difficult. So, it would be like I'm trying to think of an example, sort of like if you had a like imagine if you had a uh, box that's all sealed up and it had a bouncy ball in it, and you had to figure out where the bouncy ball was by the sound of it hitting the side. So you have to move it around to hear it, right? So you're moving it around, you hear it hit a side, and you're like, okay, it's there. But is the ball still there? No, because it reflects off and it's somewhere else now. So like it was there, but it's not still there because the act of like recording where it was like moved it. That's probably kind of the only idea that I can come up with of giving you a mental picture of what's happening. So it becomes a real pain when you're trying to figure out where electrons are, which is what they're trying to do. Okay. All right. So the quantum mechanical model of an atom. So what we found out as we're trying to figure out where electrons are in atoms, okay? We go through this idea of like, um, we have the original idea of an atom, which is just like a solid ball, like a marble. That was when they didn't know anything. They didn't know about protons, neutrons, electrons, any of that stuff. Okay, then they start finding out more things, and they have the model of an atom that is kind of like, well, actually, I don't know if you guys remember, we had the like the chocolate chip cookie model, which was basically like, um, it was like this, and then the electrons were like the chocolate chips, and then the positive was like the dough part, like that was a model of the atom. After they found the electrons, that was kind of how they thought the atom was like, and then it went from this to something like this with a positive center and the electrons orbiting. Okay. So what they found out was the more they learned about the atom and electrons and stuff, the less they actually knew where they were. Um, so the better they got at like finding information about them, they realized like, no, it doesn't quite work like that. Like they're not in fixed orbits around. They're not like that. So it's in a kind of weird twist as we gained more information, our model of the atom became more accurate, but it's more vague in terms of where things are. So this quantum mechanical model is something like this. It's basically an idea of you've got the nucleus with the protons and the neutrons, and the electrons are somewhere outside of that in electron clouds, or what we call now orbitals. Not orbits, but orbitals, like an area. So, and what they do is they say you have a certain percent chance of finding the electron in that area. So they have what are called electron density distributions, like these deals. So what these are the contour lines. The contour lines tell you the percent chance you have of finding the electron within, like, between that line and the nucleus. Okay, so like this line right here, you have a 60% chance of finding the electron in here. This line here, you have a 90% chance. Now remember, it's from that line to the nucleus. So no, you don't have a better chance out here. What, like, if I were to look in this part of the ring, what percent chance would you have? Between the first and the second? Yeah, 30, right? Because it's like 90% from here to the inside. This part is 60, which means from this line to this is 30. We added an additional 30% chance finding it here. 95% chance from this ring in. So 5 for just that ring. Right, good. So does that make sense, kind of how that works? So that's what contour lines are. The analogy I use for this to kind of help is, so if I had if I had your parents like give a percent chance about where they thought you were right now at this minute, okay? If I said, so what's the percent chance that they are in my room, like that they're in my room at their desk? Okay, that might be like, I don't know, 50, 60% chance. Okay, what's the percent chance that you're in my room? So like being first hour, that you're in my room. Okay, maybe that's a bigger percent chance, right? Because you could be throwing something away, sharpening your pencil, you could be doing a lab, you could be whatever, right? So like it'd be a little higher than at your desk. So it'd be like maybe, I don't know what I said first, like 50. So like it may be 60% chance. What if we said, like, what's the percent chance that you are, that you are in the building at Sandwich High School? Okay, so yeah, so maybe that's like 90. What's the percent chance that you are in Sandwich? 95. Like, so basically it's like the bigger the area, the bigger a percent chance you're going to be within that area, right? The more likely that you'll be somewhere within that. And that's the same thing with the electrons. The bigger the area you mark out, the bigger the percent chance that it's going to be within that area somewhere. Does that follow? Make sense? Any questions? Okay. So I know this is hard. This stuff is hard because you can't visually see it. And I try to give you guys analogies just to kind of compare it. So if it's kind of a little iffy or difficult to understand, it's not you. It's the problem of trying to mentally imagine something that's so small that we can't see it, except with very special equipment. So, these are quantum mechanical models of atoms. Okay, they've got basically the nucleus. Well, it's more like this: the nucleus, and then orbitals, which are percents that electrons are found within that area, like shaded parts. Okay. All right. Now, atomic orbitals. We already talked about, we talked about this. They're a region around the nucleus of an atom where an electron with a given energy is likely to be found. Different orbital shapes are designated by the letters S, P, D, and F. Okay? S, P, D, and F. You don't need to know all the shapes. You should know that an s orbital is a sphere and a p orbital is a dumbbell. Okay. All right. Actually, we're gonna stop here.
Yeah,
for
we
today.
don't have enough time for homework.
I was just like, okay, so